My welcome also in the name of the organizers of the event and Cloud Native Finland. We usually have a quite long presentation about Cloud Native and CNC and all of that, but I decided that we will skip that now, just we can focus on the most important thing what we will have in the future, which is KCD Helsinki. It will be a single day event for Cloud Native and related technologies in 6th of May. Very important date to remember. The deadline to submit talks is this Friday, I think. So do submit talks. You will get a free ticket and all of that if you are selected to be a speaker, and of course it's a big honor to talk in this very good conference. So do and submit your talks. If you are not into talking, you can just come and listen to the talks. We have the ticket sales open, early bird ticket sales, and
I think they already went.
Oh, they already went.
Yeah, they're gone. Yeah.
Early bird tickets are gone. Okay, so now we are.
Now you're normal bird.
Now we are running normal bird tickets. Okay, cool. Yes, but this is all I think before jumping to the meetup topics. So yeah, no, this is not all. Wait.
With regard to speaking, I would just like to say that we really want to hear from the local community what you're doing, how you're using Kubernetes or any other cloud native technology. It doesn't really have to be Kubernetes is just one of the 150 something CNCS projects.
A lot of.
And if you're unsure about how to write the abstract or how to make the process, this one, then reach out to any of us organizers. We're like 10 or something like that, and we'll get you accommodated, jump on a Zoom or something like that. Yeah, we really want to hear as many stories as possible and kind of get a diverse set of voices in the community. Yep.
Yes, and one more housekeeping request. Please do not throw your cans to the garbage cans, but collect them on that almost triangle table at the back. Thank you. And with that, let's jump to the sessions. First session is about remote attestation in cloud native environment from IAM. Yay!
Let's we do the usual thing of swapping video cables over. So this is where the laptop crashes, the monitor.
Exactly.
You broke it.
Of course I did.
Okay.
Part of my job.
What's my password? Okay, let's try. Full screen. Yay. Okay. Yeah, I'm Ian Oliver. I'm going to talk about. Well, you can read this, and this is the very, very beautiful University of Oulu PowerPoint slide theme. Isn't it gorgeous? Yeah. Okay. So I'm not a cloud well, okay, I should say I'm not a cloud person. Yeah, I remember Kubernetes being born many years ago. Anyway, but this is one of my jobs as a professor at the University of Oulu. My other job is the principal architect for Open Radio Access Network, Edge Cloud, virtualization and management at Nokia, something like that. So it's a really impressive title, which means I do an awful lot of PowerPoint. It's got architect in the... By the way, if anybody has architect in the title, it means PowerPoint. Okay. So I'm going to do this in my Oulu persona, which has really confused the security ladies over there, because I have 2 badges. Okay, remote attestation. Trusted computing, confidential computing, that's all my stuff. And I've been working in that for a very, very long time through Bell Labs and then in the universities and so on. So what do I do, or what do we do, is we ask remote attestation environments, or some kind of attestation environment, to go and ask a piece of hardware or a piece of software, are you who you say you are, and are you what you say you are? And this is then used to establish the identity and integrity of a system. Typically hardware, but we can extend this to containers, systems, whatever you want. Anything that you can measure, we can attest at some point. And you see a lot of interesting terms come up. Things that are testable, trustable, trustworthy, that's a great one. I'm sure you've heard about the trustworthy AI cloud. Okay, that's, if you haven't, that's a great way to get money out of investors. How do we establish whether a system is trustworthy? I'll come to precisely what that means at the moment. And those of you who've heard of things like the Trusted Platform module, it's not about TPM. I'll come to a little bit more of that in a moment. But this is what we do. We ask things, are you trusted? A nice way of putting this is, I've got a badge here, it says my name and stuff, and there's a date on it. This is my identity inside when I'm wandering around this building. Unfortunately, it's a complete lie. First of all, I'm not meeting this person. This is the wrong date, and I spelt my name wrong on it. Whereas this has a lot more testable information. It's got my face on it. We used to have some things like Nokia Site Day. Gerby will tell you about this. What we used to do for fun is swap our badges around. And for a while, I was wandering around. The security guard would come up and check my badge to see if I was allowed into the conference centre. Not once did he question that the fact I didn't look like a 25-year-old girl with blonde hair. He did, of course, ask the 25-year-old girl what her name was and whether, etc. But we swapped our badge, so never noticed. Okay. Okay. So this concept of trust, it's grounded in a few things, and I think you've probably seen quite a lot of this. Let's start on the right-hand side. So that's a Raspberry Pi with an Infineon TPM evaluation board. So the little black square, the arrows pointed to, that's the actual TPM chip itself. Depending upon who you ask, either it's a very small, secure environment for storing data, generating keys, random numbers, and some other interesting cryptographic operations. It's not a processor. I should point that out. Or it's something used by Bill Gates for, I don't know, giving you COVID via 5G or something like that. I mean, depends on where you go and read about these things. When it was announced that these things would be required by Windows 11, everyone started panicking. And, nope, this is a good idea. Just happened to be Microsoft doing it, which might, set a few people off. Okay, there are some terms that you're going to come across here. Trusted Platform Module, that's that little black thing, and that's basically the canonical root of trust and piece of hardware that gives you these features that you need for establishing trust in an environment. I guess you've come across UEFI, Secure Boot, if anybody hasn't heard of those. UEFI, that very, very buggy, bloated operating system that sets up your computer before the bootloader starts. Secure Boot is a term that's used where you cryptographically sign whatever you're going to start next, and then check that. Say in UEFI's case, there's a set of keys in two tables called DB and DBX that it goes and checks what maybe the bootloader or the kernel that's coming next cryptographically verifies using keys whether that has been or hasn't been tampered with. So if you go and tamper with your Windows kernel and you don't re-sign it with a Windows key that you get from Microsoft, then UEFI won't start it. The lovely thing about Secure Boot is that the moment you lose some private keys, it's game over. And that has never, ever happened 20, 30 times in history. I think every Windows or every PC at this moment is carrying around maybe 5 or 6 keys where we've lost the private key over the years. And I believe last year somebody lost a signing key from Microsoft or somewhere, which basically meant you could sign your own Windows kernel and push it using Microsoft Update and things like this. And the secure boot part of UEFI will just say, yep, it's valid. what could go wrong? Measured boot is where you actually go through the process of taking cryptographic hashes, building up Merkle trees or chains of trust. The difference between this is one of these is like saying, that's secure boot. This is like having measured boot. There's a lot more information that you can go and check against. So if you're familiar with UEFI, then you know this. I'm sure there's one or two people here who use Linux. Anybody enabled IMA? Integrity Measurement Architecture. It's a small kernel module that's already built into every kernel there is. It basically does integrity checks of the file system by generating hashes of every file on your file system, and then you can set up policies around that where if you go and read the file, the hash will be checked against the file and what's written in the database. And if they don't match up, then you can order it to just not allow access to that file. So you can detect reads, writes, and so on. The nice thing about IMA is if there's a TPM present, it keeps on extending the hashes in some of the control registers on that platform configuration registers. So if you have, say, keys on board your TPM that are protected with a particular configuration of your system, somebody goes in as a user, changes a file, it could actually lock up the entire system from pretty much the motherboard upwards, which is a good thing. TXT is a technology from Intel for doing very late attestation of the kernel, locking down CPU, etc., and things like this. Then there are technologies from Amazon, Microsoft, Nitro from Amazon, which is Amazon's version of the TPM, which it's okay. There's not enough control for a paranoid person like me, but that's fine. SGX, TDX, SEV, ARM CCA is on its way, and TrustZone. These are all enclaving technologies that we use then as part of the roots of trust, or integrate with the roots of trust from the TPM, etc., to ensure that whatever workload that we're running on that machine is what it says it is. It is actually running on that machine. TDX, SEV, for example, also have memory encryption as well. So you can load in an encrypted binary, encrypted data, have that run in an enclave so it decrypts in there, maybe only on that CPU in all of the universe. Any data that can't be stored in the L1 or L2 caches on board the chip goes out to main memory through an encryption layer as well. So you can really run very, very secure workload on there and guarantee that that will not be tampered with. There is some standardization at the IACF going around with this with RATS, the Remote Attestation Technical Specification. I'm actually part of the group that's working on some of that, and we're writing which will become the canonical Linux driver for this in the future. And then, of course, you get into supply chain security, which we'll talk a little bit about later. The other thing to also consider here is whenever we talk about trust, we're not saying that something is secure. There's a big difference between something that you know the identity of and you know what they're going to do, with them actually doing what you really want them to do. So a colleague of mine used to put a picture up of, say, a CEO or a certain electric car company and said, do you trust this person? And everyone says, oh, of course we don't trust Mr. Musk. Well, of course you do trust him. You trust him to do bad things or very weird things. So you're going to be, if somebody says, well, if you've got a TPM yet, your system can still become compromised. The difference is, I know how and why it's been compromised and what's been tampered with. And that's a very, very different piece of knowledge to not knowing what's going on. So quick question, hands up who knows if their PC has been compromised in some way from the firmware level upwards and can prove it. One is not sure. That's pretty good for these. So yeah. The rest of this is some weird notation which I won't go into. Okay. Remote attestation is basically this process. The way it fits in with things is generally, well, this is the architecture I use. Okay. I've worked on remote attestation and where it fits, where it fits into the bigger picture. So typically it's used for attesting or verifying the identity integrity of environments, trust execution environments. but it also needs to get its information from somewhere, so that's where the supply chain comes in. So if you've got manufacturers supplying machines to you, then you want to know the identity of that machine, how they've been configured before they reach you. And that's kind of the information that then we wish to attest once we receive it. I'll give you a nice little case study on that. We've done some work on forensics as well. So if you have all this information about the state of your environment, can you use that for digital forensics? I'll give you an example of that. And then we've done things like, okay, how do we integrate this with environments like Kubernetes? There was a thesis a student of mine wrote a few years ago, which integrated remote attestation, SigStore, and the Kubernetes workload management. So we could actually attest all the machines in our network, and those that weren't as trusted as we would like, we wouldn't then allow certain workload to go on those, be deployed upon those. And that's a case that we would probably get from, say, the medical domain. So if you go to Germany, they're very, very strict on how machines are set up before you can run medical workload on those. But if you go down this route along with confidential computing, then you start to get into some very nice cases where you can run workload on machines, possibly in another country, and guarantee that that workload can't be tampered with, which is kind of the panacea for, say, domains like medicine and so on. On the left-hand side, you see some screenshots. There is an attestation server that you can go and play with. It's called Jane. It used to be called the Nokia attestation engine, but we made it open source, forked it a few times, and yeah, it's now called Jane, and it's hosted on my GitHub now for lots of reasons. You can go and download it from there. The little cartoon up there, well, the truss agent is called Tarzan, and no, there is no background that I've come up with for that. But you can run, it's a small Go executable, you can run it on ARM, Intel, PowerPC or whatever, and it will go and talk to, well, it only really makes sense on Linux, because that's where the TPM drivers are, IMA, TXT, and it can gather all this information together and report it back to the attestation engine, from which then you can run verification algorithms over it and then make decisions upon whether that system is trusted or not. Yeah, it doesn't come up too well on that screen. So you can go and play with that. If anybody's interested, I can tell you something. Now, the threats that really worry me are the one, like I said, are the firmware threats, the things we can't detect. And it's quite surprising how easy these are to do and how devastating they can be. This is the box what was behind the Stuxnet attacks about 15 years ago now. Bloomberg talked about chips being put onto motherboards that could intercept data and report it back to China. Turns out not to be true, but if you're in this area like I am, that was our 15 minutes of fame. The little white box there was a thermostat that fell off a wall in a hotel I was staying at, revealing 2 Ethernet ports on the back. And then I accidentally plugged an Ethernet cable in, ran up Wireshark and a few other tools, and discovered that a lot of building information was being sent across that network. So I could actually go and change the temperature in other rooms. But the interesting thing that you can do there is that a lot of these devices are found out from the manufacturer. You could do over-the-air updates. So I can now change the firmware on this thermostat. And if you don't think that's devastating, that's exactly what somebody did at an uranium reprocessing plant. They're not too very different from each other. A few years ago, we got some medical devices, home medical devices, and we did some bad things to them. And I'm not allowed to talk about some of the things we did because I will get sued. But this company actually, they produce home medical devices which will do over-the-air updates. But those over-the-air updates are signed. I know they're signed because we found the private key on the file system. They do it over 4G as well, so I think I had a colleague here who said, well, I can put up a false base station and we can actually see what's going over the air as well. It turned out to be unencrypted. If you ever get a live stream of data off this, you get the data, and every 5 seconds it would generate a CRC code so you could check the integrity of the data. Anybody remember what CRC is? Okay, it's like SHA-256, except you can calculate it in your head. It's really not hard to do. But the entirety of the medical data on this was, the integrity of it was protected by a CRC code. There's no hardware security on this. So I can put whatever software I want. By the way, it's an ARM processor. I think it's an ARM 6. Yes, you can play Doom on it. The hardest thing, turns out, is writing to the frame buffer for the Infineon graphics libraries, which is really difficult. Last week, it came out that there were medical devices in the US that were sending all their data back to a coffee shop in Shanghai. Yeah, easy, no problem. Turned out there was also a backdoor where this coffee shop in Shanghai could actually push executables onto the machine as well. And there's no way of detecting this. If this was running something like IMA, you'd have seen that immediately and detected it. That's the picture there is from, it was the CIA opening Cisco routers at a DHL or FedEx logistics point in the US. They were opening up the routers, reflashing the firmware, and then pushing them back onto the supply chain. So customers were all getting tampered by design routers. I'm not sure what CIA would want to put on, the routers connected to the internet, but who knows. Solar winds. This is a classic supply chain issue. You can't read it on the screen. I've got some SolarWinds software. It turns out that the keys supplied with it are expired in 2020. That's a good one. And then I wanted to look up, I did the bad work, there's the evil maid attack. Look it up on Wikipedia, or you can type evil maid into Google, turn safe search off and get a completely different experience. But that's a classic attack where you push a USB stick into a laptop, allow the laptop to execute whatever software is on that USB stick. And by the way, USB sticks do not store files. There's a USB driver in there, there's an ARM 6 CPU and whatever you want to put on. It can pretend to be a storage device or a keyboard or whatever you want. So don't think that you have to go and click on an executable. You can plug a USB stick into a laptop and it can do all sorts of lies over the USB protocol and load its own software on without you knowing. The evil maid attack gets its name from, you leave your laptop unattended, typically in a hotel room. The maid comes in, plugs a USB stick into the side, maybe turns the laptop on, cleans the room. When she's done, turns the laptop off, takes a USB stick and walks out of the room. Now your machine is compromised, possibly from the firmware level upwards. And no antivirus will see that. Okay, so let's get on to the cloud because this is the exciting stuff. This is, one of these is a typical telco rack for running telco cloud operations, etc. It's really nice. So there's about 40 machines in there. These are quite old OE19s, but they're pretty powerful. I mean, who's not going to argue with something that's got 4 times more memory than disk space? When I received these machines in 2019, they were all manufactured on the same day. They were all their firmware, UEFI, was loaded on them on the same day, all signed by Nokia. When we checked them, it turned out 2 machines had different firmware. Now, over the years, I've got to be a little bit paranoid, but I'm thinking that how is it that the firmware signatures of 2 of these machines do not match any known signature that we have on our books? I'll let you figure out where we might have manufactured them. Okay. By the way, if you're wondering, no, you can't play Doom on them. They do not have graphics cards. Yeah. Okay. So once you've got all this equipment, and how does this then scale up? First of all, I spend most of my life now worrying about how I manage networks, or at least worrying about how my team is going to build software, how to manage networks. That's another thing. So we deploy in customers' premises these nice cloud environments. There's a few people from telco companies here who might have seen something similar. And we then use the classic telco NFV architecture to think about this. So there's a layer where we put our virtualized network functions. These VNFs are then run as virtual machines or containers on top of the virtual infrastructure, which means the actual physical hardware itself. We have management and operations, then of course for managing all this. Then we have the high level functions for the business support, operations support, and so on. And all this is magically orchestrated together and scale, all the nice cool stuff that you can do with Kubernetes. You can scale in, scale out, and all that. So this is how we build these systems. And what we do with these is, what I've done, is we've run the attestation server over these, collected the data off the TPMs, provisioned them, done all this setup of IMA, SE Linux, and all this. So we tried to make these machines as secure as possible, and then monitored how they behave from an attestation perspective. So when they're updated, which values change. When they reboot for some reason, how do the values change? So TPMs actually contain a counter that actually tells you how many times your machine has been suspended or rebooted. It's very important information. Doesn't sound like a lot, but you can learn a lot from that information. On top of that, then, we have the base stations, which are small servers or small computing devices in their own right, typically ARM-based. But they tend to have quite a lot of other exotic hardware in there. The latest base stations that we have ARM CPUs that are more than capable of running Kubernetes, and quite a lot of workload on top of them as well. So you can even now think of every base station that you see sitting on top of a building somewhere as a small data center in its own right. And that gives a lot of flexibility in terms of where we place network applications. Again, these things can be attested. You can talk to these and find out, okay, is this really the base station I think it is? And that's a pretty critical thing to ask. The next big critical thing to ask is it running the software we think it is? And if you think now at the operating system level and maybe even hypervisor level, we don't want that tampered with for very, very good reason. You do not want people playing with the operating system of the radio base stations that's running your telco network. I mean, what bad could happen anyway? The way we organize these then is into this concept that's called Open Radio Access Network. And there is an architecture around this that's based around the idea that we have radio units. Radio units, maybe up to 50 of them, are managed by a data unit, and that data unit might be managed, 50 of those might be managed by CUs, control units. And these are all virtualized network applications. A typical CU might be made out of, in its base form, 10, 20 containers, which then run on our hardware down here, on our NFV systems. They obviously scale up and so on, depending upon workload and so on. But the thing I want to ask of my system now is, if I can guarantee the trust of these things, can I then loop that upwards with what's running on top? So, and then from the other direction, if I've got a CU, I want to know, did that CU come from somewhere I can trust? Did it come from the supplier? In this case, this is us, being Nokia, or maybe from Ericsson or Huawei. Did it come from them? Has it been cryptographically signed? Have they provided the software bill of materials? Can I reconstruct that software bill of materials when I receive it? So a question, has anybody worked with software bill of materials, apart from that gentleman there? Have you ever reconstructed the software bill of materials at runtime? Because just telling somebody, yes, this contains genuine software, isn't enough. You must be able to reconstruct that in some form. Maybe just using cryptographic hashes, but that's enough. And what we try and organize around this now is at each point we have an attestation scheme for that. So if I want to attest a CU, I will look at its bill of materials. What value should I have while it's running and so on, and then break it up into individual containers, and then I will want to schedule those onto existing trusted machines and so on. So there's a big layer of orchestration around that where we try, it's not now about attesting individual things, but it's also about establishing the trust relationship between different parts of the system. And I can give you an interesting example now with this that we've been playing with. if we tamper with a base station, does that make the data unit that's controlling that and maybe 50 other base stations trusted or untrusted? And how do I handle that situation? What should I do? Should I shut it down? Should I sandbox it, and so on? And these are a lot of interesting questions that we don't have answers to because nobody's done it. And then, you know, if you think, well, who's going to tamper with a base station? As you can see here in Finland, we have a very, very sensitive border. I mean, you know, who knows what's happening on this side of it? So, you know, we do have a lot of equipment in very, very sensitive places. I believe on the Haparanda side in Sweden, we don't talk about that. I think you got stuff down here as well in these weird little islands. You know. So there are some very dangerous places in Finland. Mariehamn on a Friday evening apparently is interesting. So that's pretty much the static side of things. But then, you know, what's actually happening then at runtime? So, you know, at some point, images, i.e. the containers and everything else that goes with that gets generated. How do you know that those images are being generated on machines that you can trust? When you get a container, and it might have an entry in the Sigstore database or wherever, how do you trust it? Just because the hashes match up. There's another question you should always be asking yourself. What was the integrity of the development environment? And you can go ask the guys at SolarWinds about that. They were compiling their software then with a tampered compiler. That was introducing malware inside that. But then, you know, we worked on things like, okay, let's assume we've got Sigstore running there. When we acquire the image, can I then reconstruct the software bill of materials? Can I test that? When we instantiate an instance of an image, we would attest again. I think if I remember, I put little dots on this. There were a number of points where we would actually do attestation at runtime, just to make sure that even though I've got these things and I've done the attestation when I receive them, what's still happening at runtime? Are there points during the runtime of a container or a virtual machine where it could be tampered with? And that now comes down to, you know, when we want to place an instance, we need to check where it's going to run, or at least filter the machines by whatever their trust status is. When we're running that instance, once it's up and running, we're all fine. But if you get into things like suspension and migration of instances, in a previous job for a mapping company, we moved a lot of stuff into Amazon, and then we were asking the question, when we suspend a virtual machine, how do we know that when it restarts again it hasn't been tampered with? And they had no answer to that. And that was actually a security scenario that we were very, very concerned with at the time. We now have an answer to that. It's just not done, and so on. The red lines here, I mean, there's still a lot of stuff that's outside of our control. So where are we getting our cloud hardware from? Where does Amazon get its cloud hardware from? Do we trust Amazon? Or Microsoft? Or Google for GCP and so on? So these are a lot of things then we need to start worrying about. And this comes now back to where is our root of trust? Another question that's really still doesn't have a good answer is, how do we act when we lose trust in a system? If we know a component has been tampered with, what should we do? Should we reboot the entirety of the telco network and reinstall everything? Or should we start sandboxing? Should we start cutting network connections? Should we leave it running? Should we monitor it? There aren't any real good answers around that, but what we started constructing at one time, we started doing some failure effects analysis, but we started building these root cause analysis trees that gave us almost an automated way that if a failure occurs, these are all the things I need to check, and these are the actions I need to put in place to ensure the integrity of my system rather than of an individual point. I'll give you two quick examples. If you've used TPMs, they have a set of registers where you record the cryptographic measurements of your system. That's a much, much longer story. But a couple of years ago, we were running some forensic stuff I think it was a laptop of mine, I made an update of Ubuntu, rebooted, and the attestation server said PCR1, Platform Configuration Register 1 has changed. And that tells me something in the UEFI configuration has changed. The only thing that can touch the UEFI configuration is a firmware update, or a very, very low-level kernel-based approach. It turns out a single bit was flipped. And this bit, it turned out, after a bit of investigation, controlled which UEFI APIs were available. While it was in one state, the APIs were available. In the other state, they were locked from everyone. Turns out that the company that made the laptop had 3 CVEs issued a few months earlier by people using forbidden APIs to go and change things in the UEFI. You could do all sorts of weird firmware updates. So in order to get around the CVEs, they flipped the bit. But not many people do firmware updates. They're quite hard to do. So what they did was they modified part of the Intel management engine driver in Linux to go and check whether it was this manufacturer's laptop, and if it was, go get a certain UEFI variable that contained this, change the bit, write it back, and force the laptop into another reboot. Yeah. So, I mentioned reboots, and sometimes there's a value on TPMs called reset. This tells you how many times things have been rebooted. There's also PCR2, which gets changed if you enter the UEFI setup screen. Turns out on servers, this is a very interesting thing. At least on our airframe servers at the time, if you rebooted the machine, reset would increase by 1. Sometimes it would increase by 3, and the reason it would increase by 3 is if somebody had attempted to, say, hit F2 as the machine was booting up, which means that somebody's gone into the data center with a keyboard, which is bad enough. If you attempt to enter the UEFI setup screen, the machine went through a very, very long self-test procedure, which meant it effectively rebooted itself 3 times. And you would see this information recorded in the TPM PCR2 and also in the reset counter. And we could use that as a trigger to find out basically how somebody had been behaving within our data center. It also got quite interesting. So, for example, we could also find out whether somebody had tried to do this via the baseboard management controller, which is a lovely insecure piece of device that has full access to everything. And of course, if a machine does reboot, the one thing you don't want to do is admit it back to your Kubernetes cluster, just in case, because nothing bad ever happened by admitting compromised machines back into big clusters. Okay, in summary, worrying about the trust of your systems is kind of critical. And especially as we start, we're not just talking about servers running, Kubernetes, whatever, but it's the whole idea of what the cloud is, what it will achieve, the individual parts on that, and so on. The workload that's running on that. I mean, we're talking people are now talking about trustworthy AI. Yeah, this involves running complex algorithms that nobody understands on machines that we do not know the state of. But it's okay, it's in the cloud, nothing can go wrong. So I've been working on a project with Aalto. Okay, that's an MRI scanner, but there were some very nice people in Israel who went and tampered with the software on an MRI scanner and added software to it that would change the images or the data it was producing, so they could add and remove tumors from the pictures before it even got to the machine that analyzed the data. Of course, there's no way of detecting this, so good luck. So I worked with Aalto in the neurobiology unit. We have a nice machine that can change the brain chemistry using massive magnetic pulses. There are some people using it there. You see the lady smiling because she has had her brain fried. The data that we're getting back from this is very, very sensitive. And by EU law, we cannot process that in the US. Unfortunately, the company that has the brilliant AI algorithm that interprets this data is a US company, and they won't give us the algorithm back. So we came up with a compromise to say, look, okay, we can build you a machine, which is a small cluster, where we can lock down the configuration using the TPM, SE Linux, IMA. We will make certain checks before anything starts. We'll run certain firmware, certain version of the operating system. We will load your data, or we'll have our data encrypted. We will load that into a CPU enclave. Your executable will run into a CPU enclave. Everything is encrypted. Decrypts inside that enclave. We know where that CPU is. We know what machine it's running on, and we can guarantee that nothing at any point has been tampered with. And everyone was happy with that. Up until the point that says, how about we update the operating system now? And that was about a month worth of trying to reconfigure everything because cryptographic values change. So this is where we're heading to. But very, very short introduction. I can talk for another 2 hours. No, not bad. You can come and ask me questions. But yeah, this is what we do. This is fairly critical for us, and you know, this is a security area that's that people just don't know about generally. But yeah, that's it. Yeah. There's a nice thesis on this. This guy did with 6-door Kubernetes. This guy, yeah, don't worry about those guys. Some forensics, confidential computing stuff in there. ORAN security, IMA, blockchain, because that gave us money. More digital forensics, and there's a couple of PhD theses coming as well. Yep.
Thanks for that great talk. Are you using the update framework by any chance to rotate the private keys that you use for the signing?
No, nothing like that. We do everything manually because we want to see what happens. But if you have a framework that you want to test against this, yeah, we'd be more than happy to put an environment up where you can go and do that.
Yeah, no, the update framework is just document that says like do the stuff in this sort of, okay.
Yeah, we probably have some documentation on how to do this in a proper way somewhere. But yeah, we don't have specific procedures on this developed. At least none that we'd be willing to put into production.
Yeah, okay,
Yeah.
yeah. No, it sounds kind of like the OLAP is very
Yes.
significant with what the update framework has. So.
Yeah.
So, in your example with the medical device, it looks like the only thing that you could, like you don't trust your partner, they don't trust you, right? So you don't trust them with your data,
Yep.
they don't trust you with their software. So
Okay.
you would agree that you're going to run everything on this trusted machine. But it looks to me, because the root of trust is with the TPM, the only thing that you could really check is whether they have a TPM in possession.
Right.
And that, like, so if I have it, like, hypothetically, right? So if I have this chip that you showed in the beginning, I desolder this chip, and I could basically sign whatever, like, you send me the quotes, the attestation quotes, as it was on the picture, and I sign it using this chip, and you know, they hold measurements of all, like, if I have a chip in possession, that's the thing. You know?
Okay, so the chips themselves, yeah, clever people have worried about this. So every TPM has a seed from which a key called the endorsement key is generated. And that's always uniquely generatable for that chip. You can't get the private part out. It remains on the chip. When they're manufactured, they generate the EK. They pull the public part off. They, for example, Infineon and the rest of them who make these chips, they then make a certificate signing request with that. And then they load that certificate. So it's signed against their certificates. That certificate is then loaded back onto that TPM in a known place. So when you get a TPM, you'll have this chip. You can generate all this by yourself. You can go and verify that endorsement key. So you know it's a genuine chip. Okay. The EK is then its identity over a long period of time. So you need to know that for the attestation. And in the standards, in the RAT standards, the RAT architecture standard, it does explicitly state that you do need an endorsement mechanism. So somebody has to say that if you go and attest this machine, everything will be signed by these attestation keys that are generated from the endorsement key, which is verifiable against Infineon. So you set all this up beforehand, and that's where you use the attestation server. Once you've set up that identity framework, then you can start working on, say with the firmware manufacturers, what value should I see in PCR 0, 1, 2, 3, and so on, when I get this machine from the start? What are the expected values for that? Similarly, when you start loading on your operating system bootloader and the rest of the environment around that, what value should I see in the other PCRs for the file system integrity and so on? So there's a lot of process you've got to go through to ensure that you have the necessary endorsements in place before you trust that machine. So it's not a case of it's got a TPM, it's trusted. You must know what you're expecting and how you're making these measurements and how they're achieved.
Like the question is, so you trust the TPM, it means that you have to trust Infineon. So Infineon is at least a trusted party.
Yeah, okay.
Right? That's the first thing. And the second
Yeah.
thing is, okay, like if our trusted machine is some cloud, then yes, I cannot tamper with it, right? So, but if you don't trust me and you send me the machine, I still can extract not the key from the TPM, but the TPM itself and use it to
Yeah, okay. So extracting the TPM, they should, there are standards from the TCG on the hardware, on the actual physical security of them. So you can't extract them from the board. Similarly, even though at Black Hat, I think in 2015, somebody demonstrated actually chemically etching away at the TPM and reading the circuitry with an electron microscope, that was a TPM 1.2. He had help from Infineon, and it took him 6 months. Meaning that if you've got a guy who's opening up your servers and chemically etching away at them for 6 months in your data center, you've got other problems. Also, electron microscopes tend to be quite big as well. They don't fit in. But coming back to the first point is, where does the root of trust exist? Yes, I have to trust Infineon. At some point, you have to trust somebody. What you end up doing is making sure that the root of trust or the chain of trust isn't from a single point. It's from multiple points, and there are multiple points where these can be cross-checked. So if we get into, for example, Intel TTX, in order to start faking things, I need to fake things from the Intel root of trust. I need to fake it from the Infineon root of trust, from the Linux, from the operating system root of trust, Ubuntu, the firmware update, Lenovo, HP, Dell. What kinds of cross-references can I do between those, and so on. So what you try and do is to make this as damned hard as possible, to the point where it's just not economically feasible to start, pull the TPM out. Even if you did that and tried to put it in another machine, it's going to get different measurements. Unless you reconstructed the environment exactly as it was, which is not going to happen. They also have anti-tampering mechanisms as well. So on our airframes, we found that if you pulled the TPM out, it would blow a fuse on the motherboard. And the next boot you didn't get any measurements, because it wouldn't physically be able to write it to the TPM anymore. And the only way you could reset that fuse was chemically etching away at the one of the chips on the board and actually resetting the fuse at a silicon level. So, yeah, there is a weakness in here, which means at some point you have to trust somebody, but you also try and make it that you have to trust a lot of people and they all have to trust each other mutually, and there's enough cross-checks to make sure that an attack of that nature is just so damn difficult to do. It's much easier just to go and beat the guy with a spanner or something. The classic XKCD cartoon. We either reverse engineer RSA or we beat the guy up. So, yeah. Anything else? Two more. Go.
So yeah, I have have been, yes, yeah, first of all, thank you for the great talk. And the second, so when you have talking about trust and all those and open plan, how do you see the use of blockchain technology for trusting basically? It's a distributed and of course chain of command. I mean,
Are you a blockchain fan?
no, but
Good.
just,
Okay. No, it's the most dreadful technology on the planet. It has absolutely no use whatsoever. But unfortunately, to get me some research money. So, and it gets me to conferences in nice places. So, you know, I'm bribable. Blockchain. Yes, it's a very complex way of creating a Merkle chain or a Merkle hash. Do I see it happening? Well, okay, Sigstore have happened to use it in quite effectively, but the actual usage of it is, I find them very, very difficult to justify in any way, to be honest. I don't think they give you anything that you couldn't get by any other means, faster, better, and cheaper. I'm not a blockchain fan. But,
one more.
yeah.
So you open up about this SBOM. So you said you can reconstruct. So can you open up? How do you reconstruct?
How do we reconstruct? Good question. I'm waiting for the libraries to do that. Proper mechanisms and proper formats. There are some canonical formats now for software bill of materials. I don't use them. That's not my specific area. But if you do get, say, some containers or virtual machine from somewhere, you should have a record of what's inside it and be able to access that information or reconstruct that information in some form. How you do that, whether it's through generation of simple cryptographic hash or whether it's a much more elaborate mechanism, will depend upon your environment and what's available to you. Maybe there's a guy over there who might have a better answer. Yeah.
My question was actually about SBOM, is big Kubernetes specific. It's just I happen to remember that I wrote a microservice at work 3 years ago, and it does, like the build chain, it does embed SBOM in the binaries. And we actually have a third-party service scanning that in our clusters 24/7, and I had already forgotten this fact. But then the missing thing here is that while there's like Merkle tree of hashes or whatever of the everything linked inside, so you can read a single hash, like what this part of the binary and that part of the binary should look like. There's no signature on it.
Mm.
So then I came up with this stupid question now, is like, should I maybe look into Sigstore or something like, or try to have the whatever scanner scanning the clusters to verify that signature if I manage to add one?
Yes.
Yeah.
Look, two things. One, any attestation is better than no attestation.
Mm.
No attestation. Sorry, I don't speak English anymore. First of all, so if you've got a method of going to that binary and pulling out that information and being able to independently verify it, that's good. To make a claim, a piece of evidence, so I can claim that this binary is correct because here's the hash. Yeah, you do need the link then to some kind of identity, which is typically given through PKI, through signing mechanisms. So you do need that link in there as well. Which then brings up the next question is who signs it?
Yep.
And then what's the chain of certificates or whatever that takes you to that? Now, it could be that there is no nice solution here, or it could be that you sign it against say a key that's loaded onto the TPM of the machine that compiled it, and that key then comes from has a certificate chain that takes you to somewhere else, and so on. It comes very much back to how paranoid or how much auditing you want to do and how much infrastructure you want to build. But again, the question is, what's useful? We have reasons for doing this. What we don't have are good solutions, good workable extensible solutions. 6.0 is not bad. You know, you put data on there, you sign it, it's untamperable, but there's still the question of where that came from. So you just keep pushing it back. Now I can at least, I know it's come from, but, well, I can say, if I put some information on 6.0, it was correct and untampered from that point in time. How do I keep going back further? We used to call this the beginning of the universe, or the Big Bang problem.
Yeah.
So where does PCR 0 come from? Well, now we've got HP, Dell, Lenovo. They're supplying PCR 0 values in firmware updates through the LVFS system, which is great. But I still don't know how they got to those PCR values. We did ask AMI once how firmware gets compiled, and that's not an answer I'm willing to put on record, because I know some technical details of that, and it scared the hell out of me. Which is why Nokia brought a lot of firmware compilation back in-house. So, who compiled your firmware? Now you're all terrified. Now you're all going to go to Jaro and download that. Okay. Right.
Just know that a break is good.
Yes, that's
Okay, thanks.
a couple of things.
people. What's happened?
Did we break some cables?
Okay, we missed some broken cable. Just a minute. So yeah, while that's been done, yeah. And if I start rambling incoherently about AI and you have questions, just feel free to shout and ask away.
Yeah, no, it works. Yeah. It's always a
It's always
perfect
it's always the cable.
cable.
So yeah, the title is Building Scalable AI Applications for Kubernetes Deployment. But to be totally honest, I haven't touched much Kubernetes in like 8 years. And anyway, it was kind of a hard journey to relearn it again. But yeah, I guess you should get some insights of how to deploy inference-heavy workloads on GPUs with Kubernetes from this, I hope. So a little bit about myself. So I come from a nuclear fusion background in physics. That's how I ended up in Finland. I was doing a PhD with Aalto in Oxford, working with fusion reactor in Oxfordshire. Then I transitioned to AI, geospatial data. Me and my colleague over here, we worked with wildfire prevention in California, with utilities there, so a lot of 2D and 3D vision, that kind of stuff. And after that, kind of ChatGPT came out. So as everyone else, I got pretty excited, and I kind of transitioned to NLP. But today's story is going to be about like what's so important about AI that we need to do like a lot of work to unlock the data that's hidden behind corporate or institutional walls to really leverage its power, right? So I'll begin by talking about the challenges of unlocking the internal knowledge of companies and institutions. And this is kind of a twofold problem. One is obviously they don't trust to send their data to some API somewhere in California. And on the other hand, there is the problem of unstructured data, right? So there's a lot of messy enterprise or institutional data. Then I'll talk about how we leveraged dynamic knowledge graphs and my past knowledge of graph neural networks and stuff like that, and multi-model LLMs as a system to overcome some of these challenges. And then how we kind of, after creating this system, how we separated it into deployable Kubernetes microservices. And then I also wanted to kind of leave you all with something tangible. So I'll talk about some of the tooling around Kubernetes and GPUs, even though I'm not an expert, but at least I'll point you maybe in some right directions. And then on the personal front, how you can augment your own coding development, perhaps using open source models to rival kind of like closed source coding assistance and stuff like that. And finally, how you can deploy something similar to what we have, but through open source, and again, rival the state-of-the-art LLMs such as ORAN, etc. So let's get started. So yeah, so why did I go from trying to get everyone in the world free energy to saving people from wildfires to this and getting enterprise or B2B data? Well, like my strong conviction is that first of all, intelligence shouldn't be hidden behind closed APIs. It should be open source. And second of all, the data that you sent to the AI should belong to you, right? And this is what kind of drives my work. And of course, to achieve this, at the end of the day, you're going to need containerized microservices to have on-prem architecture for like large or big organizations, or these could be virtual private clouds. And you can even do some work on the edge. Like, for example, I recently got a Jet in AGX, or in which you can run some LLMs as well. Yeah, and yeah, so I believe in security. As you've seen, I raised my hand up, so like I was working with drones and AI a few years ago, and what is now named Sweden, I guess. Maybe had some hand in compromising. But yeah, yeah, and kind of the main point is that I want to drive, or that I want to convey to you, is that we should start thinking about LLMs not as these large, huge language models, but as kind of picking the right tool for the job, like you do with databases, right? If you want something light, you pick SQL Lite. If you want something big and distributed, I don't know, Hadoop, or I'm not a database expert, but you get my point. So the challenge of proprietary knowledge, as I mentioned before, there is a vast amount of untapped internal unstructured data, and it's underutilized. And it's underutilized because there is this gap between proprietary and open source LLMs. That's one reason. Another reason is that when you connect that data to an LLM, you want to be sure that it's not hallucinating somehow. You want to reference it, etc. And then you also want your deployment to be secure. Yeah, you want your context to be relevant. You want it to be integral. Well, you want to be able to integrate it into any kind of system, and you also don't want to break your company's bank doing it. So resource management. Yeah. So the first thing we set out to do is to create this framework based on open source tools like Pydantic and PyTorch Geometric to create a dynamic knowledge graph. Originally, it was meant to be a coding agent, but then we kind of shifted focus to make it domain agnostic, hence the dynamic part. What it does is it ingests various types of data. At the moment, only text data. We're working on the visual part, but basically any type of text data. It can be PDFs. It can be logs from a smart manufacturing appliance. It can be logs from some security server, like anything. Then it captures the semantic relationships and the deep contexts, and this kind of gives the LLMs the ability to reason around it and answer user queries accurately and reliably. So this goes in 4 parts. We start with file ingestion. We split data into manageable chunks. We then hierarchically summarize these chunks. So when I say chunks, I don't just mean sentences. In some scenarios, you want your chunks to be hierarchical. Say you have a GitHub repository. You maybe want to have the whole tree of the repository plus the README as a chunk, right? And then you use a smaller LLM to summarize that, and that creates a summary chunk that forms a node on the semantic graph. So once you have those summarizations, which are domain dependent and embeddings, you can then query the graph. We've implemented this domain agnostic similarity metric called DM, but you can use cosine similarity, Euclidean distance, whatever. And then, of course, the query processing is also the important part, because there is this gap between open source and closed source LLMs. It's kind of, you don't want to use just one LLM to process the query. You want to go through multiple steps to ensure that you get relevancy and accuracy that's comparable to these big tech giants. And like why it matters, it grounds the system in real structured knowledge. Then once you have this dynamic knowledge graph, well, the next thing we did was build a multimodal system. So basically what we have there is we have 3 different models. And what we found was that the size of an LLM matters a lot in terms of how or what you use it for. For example, around like 32 billion size is particularly good for converting unstructured data to structured data. 70 billion from the open source community, like Llama to be precise, is particularly good at taking not such a good but contextually accurate answer and formatting it nicely for the user so they get the nice user experience. And then also we have a third model, which is like a long context, 100,000 tokens long, which contextualizes the conversation. So basically by creating this symphony of models, you can emulate what the closed source providers do. And this is all kind of behind an API, which is OpenAI compatible, and yeah. But then so then we built this big monolith, and the challenge was like how do we deploy it? And we realized that we can't really deploy it as a single deployment, and we had to split it into microservices. This meant that because Kubernetes is not designed for GPU-intensive workloads, we had to create some custom scheduling and queuing systems. We use VLLM as the inference engine. It's also prone to crashing. All of this work is kind of like very much work in progress. So we had to do a lot of our own bespoke solutions. But basically we use containerization with custom queues and scheduling. And then we employ asynchronous stateless services to maximize the GPU utilization. So basically, like, my aim is to keep that GPU utilization graph at around 90%, and that makes me happy. Yeah, but I should also say that open source projects like VLLM, they're getting more and more kind of developed. So more of this kind of scheduling stuff is getting offloaded to the inference engine over time. So I wouldn't, like, if you're getting into this right now, I wouldn't spend time creating what we did. Like, it's probably in a few months, VLLM is going to release something that's totally stable. So I kind of there's a lot to talk about in security, CI/CD, and modern MLOps integration, but I try to narrow it down to the kind of most interesting things, or most recent and interesting things. So first of all, you want to have, when you have an LLM model or an LLM system, you want to make sure that you have integration tests, right? You also need benchmark tests to check for regression, and you might have some domain-specific tests from clients. and all of this is quite heavy. So, but you can leverage GitHub Actions to spin up some spot instance to quickly do your CI/CD. And one thing I wanted to highlight here is that VLLM recently released this tensorize your model feature, which is kind of cloud agnostic model, which enables cloud agnostic model version control. Originally designed for S3, but it works with any kind of blob storage, but it allows you to encrypt a model, and it also allows you to pre-compile the model so that it instantly kind of shotguns from cloud storage to RAM to VRAM to GPU, which is quite novel and interesting, and allows for encryption of the model, so it can't be tampered with. Of course, you still probably should do some checksums around it or something. But yeah, so LLMs as COGS in a larger system, as I mentioned before. Yeah, my point being is that we're transitioning from this isolated, monolithic, large language models to integrated modular components within larger systems. And again, like databases, large language models operate quietly in the background, powering diverse application. And why it matters is that it unlocks kind of the power of open source to rival what's behind closed doors in California. And then yeah, so now to the tangible takeaways. I think the tensorization maybe was one. Another one is I guess in the past few weeks there's been a bit of a paradigm shift since the, I don't know, how many of you have heard of DeepSeek R1? Yeah, so there's been a bit of a paradigm shift. But basically we're moving from large language models to small reasoning models. And this is kind of an overlooked thing in the DeepSeek R1 papers, where they fine-tuned, for example, Qwen 14 billion, which is like an order of magnitude smaller than R1, and it almost rivaled O1 mini. You know, so basically the reasoning is getting separated from the knowledge, and that means that kind of these classical knowledge graphs are becoming more important, and the reasoning engines are likely going to be separate. And what that means in the context of Kubernetes is that in the past, things like time sharing and QU, which is also a Kubernetes project, which is a bit better than NVIDIA's time sharing because it allows basically idle tenants flops to be allocated to non-idle tenant flops. But basically this whole paradigm relied on prompt caching, i.e. you put in your documents and they sit there in the context, and you benefit from prompt caching, cached prefill, page detention, all those things, right? But with smaller medium reasoning models, there is a constant I/O of reasoning tokens, so input and output, because they're constantly reasoning. So you can't prefill your batch inference chunks. You can't do prompt caching, and this means that likely the future is in MIG, which is multi-instance GPUs, and the link here is to the NVIDIA implementation, but there's also an AMD implementation of that. Okay, and then okay, so what if you want to develop a coding assistant that, say, rivals O1 mini on your laptop or on your computer at home if you have a graphics card. You can take together projects like, for example, Aider, alongside tools like OpenRouter and the recent distal models from DeepSeek R1, and achieve competitive results in coding benchmarks. There is another library called OptiLLM, which basically takes a lot of these Monte Carlo tree search, R-star, chain of thoughts, chain of code, etc. algorithms, and allows you to basically route a model to do that before it creates its final answer. Then there is also the simpler tools like All-Online LM Studio, if you want to just get into playing around with LLMs. But my point is that I think now is the time to kind of start leveraging these open source techniques, because, well, it's becoming quite clear that open source is catching up. And here's, by the way, example of me trying to reconstruct my Obsidian vault with Aider. Then what if you want to build your own knowledge and chatbot system? This is the library I mentioned, which has a lot of these optimization algorithms, which let you concurrently or sequentially scale the inference compute of your local LLM, and you can couple it with something like OpenWebUI, which is a leading kind of competitor to ChatGPT web interface or Mac app or Claude. It has artifacts, it has integrations with RAGs. It's secure. You can use it on your own laptop. You can encrypt everything, all your data. So do try it out. And like, is it possible? And yes, it is. And I'm gonna try and do a demo here. So this is not even a reasoning model, but this is Qwen 2.5 code of 35 billion. And the prompt is visualize the NVIDIA stock dropping by 15% after market opening post DeepSeek R1 release. Let's see if it works.
Have we come to the point that LLMs can now center something that already learned?
Sorry?
Did we get to the point now that LLMs can center a div in CSS, something humans never could?
That's what I've been struggling before this presentation. That's where all my diagrams are off. So there you go. So, and this is completely open source, and you can replicate this with OpenWebUI. Yeah, so to kind of go towards the future directions and emerging trends. So, as I'm repeating myself again, but these distilled reasoners can be highly efficient, although they lack contextual knowledge. But they're going to keep getting probably smaller and smaller and run on smaller and smaller devices, and all you have to do is connect them to a knowledge graph. And I believe Google released the knowledge graph concept in 2012 or something, so it's nothing new. Yeah, and the kind of interesting, surprising, a little bit scary thing is that you see this graph where they were training DeepSeek R1. They kind of stopped, but it keeps going up. So the future is a bit uncertain in terms of how far we can take these reasoners. But the idea is to build systems that integrate these reasoning engines Also, you can treat LLMs as data structuring engines, and basically access untapped data in industry, enterprise, institutions to make the world more efficient and maybe get us through whatever the hell is going to happen. But yeah, thank you. Yeah.
So thanks for the talk. Two questions. So I guess you were pretty relieved when preparing this talk in beforehand, and then DeepSeek released, kind of proving, confirming your thesis.
Yeah.
That's nice. The second thing is about the knowledge graph and authorization or access control. Have you are there some emerging trends there on building in the existing access control paradigms that we have in our systems into the LLM, understanding that this specific person shouldn't be able to access this part of the graph?
Yeah, like our current implementation is basically it plugs into a PostgreSQL database, so you can manage access on that level, but maybe when the reasoner is improved to the point where you have, I don't know, 0.9 of reliability, you can create action tokens to decide whether this person should get this access or that access. That's kind of my viewpoint. But at the moment, yeah, it's still databases.
Okay, thanks.
Yeah.
What do you think of, so I know a couple of companies that are doing this context memory for LLMs. One of them called Letta.ai, it was MemGPT before, and another one is called GetZep. So Zep is basically a knowledge graph that is reconstructed on the fly from the conversations and stuff like this. Have you tried any of this?
Yeah. Actually, the conversation is part of the knowledge graph in our system. Yeah. And actually, did you say MemAI?
MemGPT.
Oh, okay. Because I've used a product called MemAI before as well. That used kind of knowledge graphs. It was kind of a combination of Obsidian and LLMs. But yes, yeah, I've tried that. Yep.
I'm sort of interested in your use case with performing a knowledge mapping on your Obsidian vault. So could you maybe talk a bit more about that? And is the knowledge mapping sort of almost one-to-one, like the links in the tag and so on, or how many does it take a lot of compute to perform the summarization of your notes?
Well, what I did there was I duplicated my vault to have a backup, and then I basically let Ada run iteratively, just saying yes, do this. Well, I gave it an initial plan to structure how I want my thing structured, and told it to yes, keep going. And it created something, but I took the screenshot fairly recently. I haven't tested the final result yet. but I do like to run these tests to see how far you can kind of push these systems iteratively. And this was using DeepSeek SAR1. Yep.
Final question maybe. Have you tried out Kubernetes dynamic resource allocation feature? Does it help? And if so, does it help all the GPU scheduling and stuff when that's one of the features set to enable that?
Yeah. I'm not the right person to ask this to be honest, because I couldn't answer this question. Sorry.
Yes, no problem.
Any other questions?
Well, I have a kind of a question
Yep.
or view actually. So the first one will be related to the MIB, so or MIG actually, mix.
Yeah.
Who should configure that, for your opinion? Is it the ML or AI engineer should think about it in the first place, or just offload that to infra team to like actually spin up the Kubernetes infrastructure for that particular project?
Well, our idea is that we kind of we take that load away from you, because like it's a pain in the ass. Like there is so many like inference engine parameters, and then you have to make sure that it works with the chunk of the GPU and the size of the model and the KV cache. So the idea is that we kind of do that job. We create some templates for different domains, and then and kind of there was this quote in some recent podcast that IT is the new HR of AI, you know. So the IT department would kind of take these examples and use the OpenAI compatible API to configure an assistant, say for the sales team to create a sales agent or something like that.
So basically, ML engineers should like configure everything, make some templating.
But there is I feel like there is some feedback loops. Like once you have enough templates, you can also get an LLM to iterate on the templates, and also there's frameworks like the SPY which help with prompt engineering.
Yeah, I'm kind of asking that question because out of my experience that AI, ML, whatever, engineers actually have no idea how the big clouds are made, and they like completely out of any knowledge what type of a nodes they should like take for their load, for their pods in the Kubernetes. But the infra team who is supporting them may support them. They have no idea like how that AI stuff is actually working, and that's one of the big issues. And another big issue, I must say, what in GCP and Azure and in AWS, there are like different ways how you can configure your nodes with the GPU.
Yeah.
So you basically have to have at least a few people who understand how it works, not just one or two.
Yeah.
Because like if you choose just NVIDIA cards, just for example, then implementation of how to use them in AWS and in Azure are different.
Yeah, and actually because like we're a small startup and we get credits from all three clouds, I went through the pain of not knowing and trying to set this all up. LLMs help to a certain extent, but it's still like grueling work. Because if you think about it, like every one of these big tech giants have their own LLM. And usually their own LLM knows how to configure their cloud to some extent. Obviously it takes a few iterations, but also like to come back to your point of DevOps teams working together with AI teams, I think that's an excellent point. That's exactly what our company is, kind of 50-50 split on almost.
Okay.
Yeah.
Yeah, and also just a comment, like I've been on the Databricks Cloud Days, wherever, in Stockholm last year, and there was that technical director, the CTO of Nova Nordisk company who made Ozempic and made all the money of the world at the moment. So they actually already switched to that mini agents model in their infrastructure, working for hundreds of thousands of people working their system. And well, I think I must share, in our company we also switched from the bigger LLM models to a few quite smaller but specialized.
And I think the like Elias Asker's super intelligence, his aim is to probably like to separate that reasoning layer from the LLM itself, because there's no point of having all this knowledge and consumes GPU resources if it hallucinates on it, right? Instead, you can have a knowledge graph which eliminates that, and a very good reasoner on top of it. Yeah.
Okay,
Cool.
Right. Thank you, everyone.
Let's have a, let's say, 10 minutes break, and then we will continue with S-bombs, if I remember correctly. More S-bombs, yes.
Sorry.
I can do justice to whatever he said. I'll be talking about software supply chain security. Let's dive deep into it. A software supply chain is essentially all the steps that are involved between a developer building a code, testing, securing, and ultimately deploying on any sort of servers, clusters, whatever, right? These steps are usually build, secure, test, deploy. Fairly simple. And yeah, it would include end-to-end workflows, security, integrity, automation, and compliance. Well, now that you understand what a software supply chain is, what if your supply chain was compromised tomorrow? We've all heard about, or we've all seen, the famous CrowdStrike blue screen of death that happened last year. That was a vulnerability that was pushed to a production level code. It caused system compromise, RC, that is remote code execution, data theft, and all sorts of other damages. XZ utils is a peculiar one. A malicious actor inserted a backdoor into one of the distros of Linux, and it was sent out. And there were, again, problems of code execution, denial of service attacks. Log4j is, again, pretty famous. I think it came out in 2021. It had similar problems of RCs, supply chain attacks, cryptojacking, all of that. What we learned from all of this is that your code is never 100% secure. You can take all the precautions you need, all the necessary steps, but then you just have to hope for the best, right? What, according to me, is a secure software supply chain? I would include these three basic steps. Zero CV base image. I've written almost, we will get to that later. Robust systems, be it build, deploy, whatever. Signed and verified artifacts. Yeah. Is there? Why? Am I stepping on something? Medium CV, we also want to make sure that our systems are secure, be it the developer environment or the CI/CD system itself, or the target Kubernetes or any sort of service. They should be secure under at least three elementary steps, right? Network isolation, role-based access controls, that is RBAC, and also access control lists of any sort if you're using a cloud provider. What does signing an artifact achieve? Almost a year ago, a senior of mine asked me, how do I make sure that the artifact that I build is the same that's being deployed, or it's the same that's being consumed? I was quite naive, and I answered that, well, we have a multi-stage pipeline. It builds, it tests, it secures, it deploys. So does it not mean that whatever we build is being deployed? I found out that the answer is no, again. Artifact signatures are one way to achieve integrity, authenticity, and provenance as such. The cloud native way to go about it is using Sigstore, as Ian mentioned previously. Sigstore to sign, you can also verify with Sigstore, but if you're using a Kubernetes deployment, you can use open policy agents, say like Kyverno or admission webhooks to verify the signatures that Sigstore generated for you. I have a short demo that will cover a couple of things. I have a GitHub Actions that does two jobs. It builds an unsigned image, it builds an image, and it just pushes it without signing. There is also a signed image job, which builds it. There is a Trivy job that creates an SBOM report out of it, and then it pushes to the registry. Once it's in the registry, Sigstore fetches it and signs with a public-private key encryption. I also have a small deployment. I have a Minikube cluster running locally, which tries to apply these two images. And we shall see what happens when we deploy an unsigned image versus a signed image. Okay, before that, why? Okay. I talked about ChainGuard, or at least I displayed ChainGuard, right? So ChainGuard is where you can find 0 CVE base images. I picked out a sample BusyBox image and wrote a Docker file which just says hello world, right? And then
I can hold the mic.
that's okay. Let me show the pipeline. I'll be running the pipeline. I have previous runs just in case it fails today, like how the cable is failing sometimes. I'll just show what each of these jobs are doing, right? In the unsigned job, I have these steps. I've set up a Docker buildx instead of a normal build because I'm using the type OCI. I think OCI format is pretty essential in the modern day architectures because OCI is platform agnostic. You can run OCI images on all sorts of platforms, and OCI format should be the standard for running Kubernetes applications, right? And then, yeah, I'm using the GitHub container registry to store these packages. During the signed image job, it pushes a signature to the same registry. So here you can see once it's signed, there is a record that's created. It's called a T-log. That's over here. This is a transparency log. Sigstore has something called a record transparency log. If at all an enterprise builds an image and signs it with their private key, and you're verifying it with the public key that's available, you can make sure that transparency log index matches with whatever they signed. I'm also verifying it locally so that I just have a record of it. You can see that I think this is the index. It's the same as whatever is here, right? Let me go. Was it not?
It was the next one.
Okay. Okay, I think I pointed to the wrong thing. Coming to the packages, I have these two. That is a signed image and an unsigned image. Unsigned. I'm generating an SHA tag, an SHA short tag as the image tag. Sigstore signatures need an SHA digest of the image in order to be able to sign. And I found this quite convenient. When I moved my signed image along with the tag itself, there is also a .sig that's been uploaded to the registry. Right? Let me see if the action is complete. Cool. And the latest. Package. Okay. Unsigned image, it is this. I'll copy this. I'll go back to, this does not have it. I'll go back to my VS Code. Okay. I'll replace it here so that I make sure that it's the newest image. It's the same tag that's been generated for both the images. Did I copy something else?
It's old one. Yeah, it's 2 days ago. Previous. It's not the one you just built.
It is. It is. Okay. Cool. Okay. Now, I will also show the cluster policy that I have. This is a Kyverno cluster policy. It makes use of the cosine public key. Cosine can generate a public-private key pair with which you can sign your images. You can also store these keys in any of the cloud provider key management system. I'm doing it locally for the purpose of this demo. Now I will bring up terminal. Okay. Right now I have nothing running. Now if I apply an unsigned image, it tells me that my request failed. It denied the request because of the following policy: no signatures was found. If I do it with a signed image, oops. Yay. Right, so my image is running, and if I see the logs, it says hello world. It just says world, but you get the point. Yes, so what did we achieve? We had an OCI format image. We signed it with a public-private key encryption. We tried to deploy an unsigned image versus a signed image and saw how a cluster policy can allow or deny said requests. Additionally, this would be the way forward for people who are trying it out at production levels, right? There is something called an SLSA. If you've not heard about it, it's supply chain levels for software artifacts. It's a security framework or a checklist of standards that controls and prevents tampering of software artifacts. It would essentially contain software bill of materials and attestations. Software bill of materials reminds me of this. This is how a basic SBOM would look like. Okay. It would contain all the information. Let me pull this. Okay. This is the image that I built, but then we can see what all it contains, right? I have a BusyBox image, but what all does the BusyBox contain? It would contain all these libraries. I think what Ian meant in reconstructing an image out of SBOM is basically taking the base layer and maybe adding utilities to it so that we can achieve a similar sort of container image to deploy the application with. Right. That was about software bill of materials. Attestations, Ian spoke a lot about it. I won't be getting into it. References, yes. These are some of the references that I took in order to give this particular demo. AIMUs. I really like creating the slide. So when I was preparing for the demo, I asked a couple of LLMs to generate a diagram for me that depicts software supply chain security, right? You can see that the images look very complicated. They have a lot of elements. They have so many things, mostly unwanted things. Can I zoom in? Let's see. Does it allow zooming? Yes. When you see what's written inside images, you see that it's total crap. there's a tepsting, there is a diplotian. I don't know, there's a bunch of things that shouldn't be there. And I don't think the picture as a whole makes sense even. These were two different LLMs, and I just wanted to show it so that, I mean, I don't have a point, but then it's just funny.
Yes.
Yes, well, thank you so much. So this was my first ever tech talk. I would really appreciate the feedback. It's just a small Google form. Really appreciate it if you guys can give a small feedback. Any questions? Yes.
Yeah, well, I tried all the stuff already a couple of times. But yeah, thanks a lot. That's basically it, how it should be. But have you ever tried to think of trying doing the same procedure on scale? I must say, when you're like simultaneously building like hundreds of images, for example.
Okay.
For me, the 6 store was not reliable.
I think there are a couple of more open source alternatives. When I was doing my research, I don't remember the exact names, but we can talk about this later. Sixstore might not be the only tool that can do signatures and verifications. There are other tools out there, but Sixstore might be the most recommended one.
Yeah.
At scale, I am not sure how it performs.
Yeah, because, well, we tried that our, let's say, CI, and some of the reasons we create like x86 version of an image, so not just one big one, but the x86 and IRM64, and also then we add the S-bones there, so it's another kind of a push to the ACR. Then the first signature, then the attestation. So there are really a lot of requests to the SIG store. And when you do like hundreds of images, well, maybe not like in the same second, but in, let's say in an hour or something, the SIG store just started to think that you're trying to DDoS them.
Okay.
So
yeah, I think that's a fair assumption.
Yeah.
Okay. Yeah, I haven't given it a try.
Yeah, and another question, well, not the question, but basically the same thing, but when we do that exact building in CI, so literally instead of like, let's say, 3 different well, images in our ECR, we actually get like 9. Because it just, the actual image, well, I'm talking about the AWS, maybe in GCP is a different and Azure is different, but in AWS you'll get the SIG kind of image. It looks like an image. Of
yeah,
course,
exactly.
It's
Yeah.
very small, and eventually, and you can in some of the cases quite fast reach the limits of like 10,000s of images.
Okay.
Especially if you do like rebuilding very often.
Okay. That's an interesting.
Yeah, that's the question, which should be kind of a.
AWS has their own signature and verification sort of tool. AWS native, there's a tool. Forgot what it's called. AWS Signer, I think.
Yeah, they have something. Yeah. But if following just like the same procedure what you showed to us, the demo, that will.
Maybe it might not work at that scale.
Result in like in thousands extra images, which maybe will not be really convenient for your like life cycle policies. It all depends on like how you configure them, of course, but it can be a problem just for your next version of the presentation.
Yes, I will take into account. Thank you. I had a question. I think there's another. Oh, there's a question online.
Question online. Yes, it happens very rarely. What was the most interesting thing you learned while preparing this presentation from Steve?
Oh.
At Cloud Native.
Okay. What was the most interesting thing that I learned about it? I initially sort of developed a talk where all the elements of my demo was manual. I had not thought about encapsulating all of it into a GitHub action or like a pipeline. I think I sort of got that direction from maybe Steve himself. So and that really helped me add more things, make it more streamlined so that it can look like an actual demo instead of me just running hundreds of Linux commands on the day. Yeah.
Thank you.
Yes.
Yeah, thank you for the speech. Do you know what the algorithms are used for, like actually how the signature verification works? Have you checked that? And yeah, basically that.
Signature verification themselves. I believe they use SHA-256 algorithm in the background, but I am not entirely sure.
Because I noticed on your piece, maybe I didn't pay attention, but it was like the image is signed and signature verification is correct are two different things. So you could sign the image with another private key and try to check if it works, like if it's gonna fail as well.
Well,
unsigned image and this differently signed image are different things.
right, but the image that was signed, whatever private key which was used, I used the public key that was attached to it in my cluster policy.
Yeah, but have you tried, like, because you just rely on the, how can I say?
Yeah.
Okay. Because, like, if the algorithms are not strong enough, it's, I would say not impossible, but possible to actually make them collide and you will get the success.
Maybe, yes.
Thank you.
Thank you. Cool. Thank you so much.
Thank you very much. So yes, these were all the presentations for today, but we are free to stay until 9ish, so you can just mingle and ask questions about the case city. There are stickers also near these sodas, so but enjoy and talk to each other.